Okay, hi everyone. Okay, so before we discuss this question, a few things about. Okay, sorry. Can everyone hear me? First of all, sorry, I'm always paranoid if the connection is holding or not. You guys can hear me, right? Okay, sweet. All right. So before we discuss this question, just a bit of important kind of um, understanding of what happens when a robot is moving and what happens to the laser scans, right? So imagine let's say there's some sort of wall, right? Let me go here, right? So imagine there's some sort of wall, and we have a robot that is facing the wall, right? So imagine this is the front of the robot, right? I'll actually put a little dot in the front, right? So imagine this is the LiDAR, right? The laser scan. So it will scan this wall, right? And in the coordinate frame of the robot, right? So this imagine this is the global coordinate frame, right? What I'm drawing above this blue line is how the robot's basically everything relative to the global coordinate frame, right? But from the robot's local frame, right? That is okay. So let's, for example, say this is the global coordinate frame, right? But all your measurements will be coming relative to your robot's coordinate frame, right? So how the robot will be seeing it is through this lens, right? It will be looking at it in this coordinate frame, right? So we will always pick, for example, the x direction of your robot as the forward direction, right? So this is your global frame, and this red thing is your local frame. That is everything how the robot perceives it in the local frame, right? So if you look at the local frame, what the wall will look like, right? So imagine this is the robot, right? And it's x and y, right? It will have a bunch of points like this, right? From its laser scan. Now imagine in the next minute, right? So, right, this is, let's say this is at time instant t, and then we look at time instant t plus 1. Imagine the robot has now kind of rotated in one spot, right? According to the global frame, remember this top half is the global perspective, like everything according to the global reference frame, right? And what I'm drawing here at the bottom is a local frame, right? So in the global frame, this wall doesn't move anywhere, right? According to this reference frame, the wall will still be here. But our robot now has rotated, right? So now its scan will be somewhere like that, and in the local coordinate frame, according to the robot's sensors, right, that's fixed. This is the robot in this time instant in x and y, right? Now the scan, because the robot is rotated, will look something like this, right? Yeah, if the robot's over here, this point will look so blah 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 blah, right? Yeah, we'll have something that looks like this, right? The wall will look something like right. So when the robot rotates, the sensor information, the scan that you're getting has now changed, right? There is a transformation from where it was before to how the scan is being received by the robot when it rotates, right? So the robot perceives things not in the global frame, the robot perceives things in the local frame, right? It's getting sensor information relative to it, right? So the information that it will be receiving will look like this, right? So if you can somehow find the transformation between this wall, right, and then how it appears to the robot, you can kind of figure out how much the robot has rotated, right? What I mean by this is basically for the robot, from the robot's perspective, it doesn't know whether it's rotating or not, right? The only way it can know whether it's rotating or moving or whatever is through sensor information, right? Because it doesn't have a concept of what the environment is like, right? Unless we give it that concept, unless we have a map, and then we take sensor information from the environment, and then we have to explain, like the robot has to figure out that it has rotated, right? And the way it can do that is only if it had a map and it has the sensor information, and basically figure out the rotation between where it was before from its sensor information and where that sensor information is now, right? So when it sees that this has pretty much rotated, it knows then that it has rotated itself, right? So this is why sensors are important, right? Sensors give you not only information about things like obstacles and so on, it also helps you kind of figure out how you're moving, right? Sorry. So there are multiple sensors that give you that information. So you have things like IMUs, you have things like encoders on your wheels, right? All of these sensors give you information about how you've been moving, right? And since sensors are noisy, none of those answers are generally completely accurate. So what most roboticists do is we get information from multiple sensors, and then we fuse that information together to come up with a better idea of how the robot has moved, right? So generally what you would do is you would take encoder information, you would take IMU information, you would take laser scan information of the environment, and then kind of figure out how the robot has kind of gone from this to this, right? Because it has no concept of the global reference frame unless we provide a map and then the basic sensor information to match it with the map to figure out how much you moved or not, right? So it's really important for a robot to figure out these transformations, right? So what we've done in this question is basically given you two scans in two different situations, right? So from the robot's perspective, it hasn't, from the robot's local frame, right? It's fixed, right? So the robot will always be having its x-axis forward and y-axis up here, right? So it's so whenever you define a reference frame, that reference frame gets fixed, right? You're looking at things from its perspective, right? So it's kind of like if you're in a moving car and you didn't know that the car was moving, right? It will look like your environment outside is moving rather than it's the car that's moving, right? So motion is ultimately relative to a given frame, right? So from the robot's frame, the robot is not moving, the environment is moving, right? But by the movement of the environment, you can figure out the actual motion of the robot, right? So that's kind of what we are really aiming at here, okay? So imagine these are two different scans given in the same reference frame relative to the robot, and the question is how has the environment transformed, which will give you an idea of how the robot has transformed, right? So can a few of you guys just tell me what has kind of happened in terms of translation and rotation? You can either use the chat or use your microphone and just tell me by just looking at these two images, how has the robot rotated between time t1 and t2, or how has it translated? Anyone? Nope. Okay, so you can see that this point, for example, is over here, right? So what has happened essentially is this, not really. So it's actually rotated 90 degrees clockwise, right? So it's gone from here to here, right? So it's actually a 90-degree clockwise rotation, and it's also translated one up, right? Actually, no, wait. Actually, you're right. It's this point that's over here, right? Yeah. So it's actually rotated 180, correct, right? 90, 180. Yeah. Actually, it's either 270 clockwise or 90 degrees anti-clockwise. Correct. Liam's correct. Yeah. Liam and Harrison are correct. So it's either 90 degrees anti-clockwise or 270 degrees clockwise, right? Yep. Yeah. Okay, so from that you can figure out that the robot has rotated the other way around, right? For the environment to rotate that way. Okay, so from this example you can see that you have to use your brain's processing skills to kind of figure this out, right? But we need to be able to do that using some sort of algorithm so that a robot can do it, right? So what most people use is something called ICP, right? So ICP stands for iterative closest point. So our next question is going to be about ICP. It's about how you can do what you just did by how you visually analyze this and use your brain to figure out the rotation and translation, how you can do that using an algorithm, right? So what ICP does is basically, I'm not going to spend too much time explaining in depth, right? But how ICP basically works is, so imagine in this particular example, right? We had the two scans look like this, right? What it first does is it finds matching points, right? Actually, we'll use this example that I gave you guys, right? So, give me a sec. Let me try and. Right. So what ICP first does is it finds matching points, right? So it has to figure out that this point, right, is actually this point, right? Right, and then this point is actually this point, right? So first it finds these matching points, right? So once it finds these matching points, it tries to minimize the some sort of metric that captures the difference in how these points have transformed, right? So usually that metric is something like Euclidean distance or something like that, right? So what it does is, imagine it says that this point and this point and this point and this point are matching points. It calculates these distances, right? It uses some sort of metric, so you can change the metric depending on how you want to do your optimization, right? And what it does is it tries to minimize the transform between, it tries to minimize this distance under the condition of a transform. Like, what's the optimum transform you can get that minimizes each of these distances, right? So it does some form of optimization to minimize that metric and find the transform under which you will get the optimum result that minimizes those distance metrics, right? So what you end up getting is the transform between this scan and this scan, right? So once you have the transform between these two scans, what you can do is figure out the transformation of your robot, right? So the transformation that you'll be getting is a 4x4 transformation matrix, right? So we already discussed transformation matrices, and I think, yeah, we used them when we were doing like projection and things like that, right? So it has a rotation matrix here, a translation, and we usually have this transformation matrix in some sort of homogeneous form, so we can kind of chain them together, right? So that's what ICP does, right? So what we have in this question is an example of using ICP to figure out this rigid body transformation between two point clouds, right? So a point cloud is basically, think about the depth information that you have in a laser scan, and imagine we project it out into 3D space, right? And then have each of those points. So that's pretty much what a point cloud is, right? So I've given you guys a text file with laser scan information. I want you guys to load it onto MATLAB, right? And obtain the first and 32nd laser scan, convert it into point clouds using MATLAB, right? So I've given you links to how to convert it into point clouds. And then once you convert it into point clouds, which is a point cloud is basically a 3D projection of those depth information that you have. I want you to use this function PC register ICP to use ICP to figure out the transformation between those two point clouds, right? I'll give you guys like 10 minutes to do this. You can use these links to help you guys, like it has all the instructions on how to do it. Just try and give it a shot. First you'll have to load this text file into MATLAB, and then just follow the instructions in the question and see if you can kind of do the question, right? I'll give you guys like 10 minutes to try it out. All right, you guys, let's run through question 3. All right, so we have a text file that's Intel _laser _text, right, which has a bunch of laser scan information. So if I actually open it up, where is it? Yeah, there we go. You can see that it's just a bunch of range values, right? So each of these rows represent one scan, right? So you can see that there are 2,726 scans, right? And each of these values in these rows represent the range values per scan, right? So this is scan number 1, this is scan number 7, and so on, right? So what we need to first do is we need to load that information into MATLAB, and you can use this function load to load any text file onto MATLAB, right? So I've used load to load it onto a variable called scan. And then I'm going to use the same trick I did before using this function linspace to find the angles that correspond to each of those ranges, right? So we've been given that there is a field of view of 180 degrees ranging from -90 to +90, right? So I'm using linspace saying -90, +90, and I'm dividing it into 180 different parts, right? And then the question says, take the first scan and the 32nd scan and convert it into a 3D Cartesian coordinates, right? So that we can create a point cloud object out of it, right? So I'm first going to take the 32nd scan and the first scan out of these scans that I have, right? And what I'm going to do is I'm going to convert each of these scans into Cartesian coordinates first, right? So in this case, I'm going to use the pol2cart function, right? You can also do the same thing we did in the previous question and just multiply each of the scan values by the cos and sine values of the angles, right? Just like in question 2. But just to show you how to use the pol2cart function that I've suggested in the previous question, I'm just going to use that. So what that does is when you input the angles and input the scan, it gives you the x coordinates and the y coordinates of that scan, right? So I now have the x coordinates and the y coordinates of the first scan, and the x coordinates and y coordinates of the 32nd scan, right? Now what I'm going to do is I'm going to convert it into point cloud objects in MATLAB, right? So to do that, if you look at this, basically, if you go to this link, right, it should give you information about how to make a point cloud in MATLAB, right? So if you go into this link, basically what you need to do to get a point cloud is give the x, y, z points into this function called point cloud, right? And it will create a point cloud object out of that, right? And basically there's a whole bunch of functions that you can use to display those point clouds and so on, and all that information is in this page, right? So at this point, whether you're using ROS or MATLAB, you need to get used to going through documentation like this, looking at the available functions and seeing how to use them, right? So if you look at the syntax, you just say point cloud and give the XYZ points, right? And you can see that one of these XYZ points, right, the format of it is it's a m by 3 list of points, right? What that means is it has m set of rows and 3 different columns that represent the x, y, z values of each point, right? So from our previous pol2cart function, right, we got the x and y values out of our 2D scan, right? But a point cloud object needs 3D points, right? Not just 2D points. But our laser scanner is a 2D laser scanner, right? So what we're going to do is we're going to set the third z points just a bunch of zeros, right? Because we don't have full 3D information, we only have 2D information, which means our z-axis values are 0, right? So what I've done is I've taken these x, y values, right? And I've set the z values, I've created a new matrix with the x, y values, and for the z values, I've just put a bunch of zeros using MATLAB zeros function, right? So I've given, so there's each scan has 180 points, so I've just made a bunch of zeros, right? You can see just a bunch of zeros, right? And the other small caveat that you need to be aware of is when you turn this pol2cart function, this scan 1x is a row vector. So if I type scan, if I run this, give me a sec, right? So if I comment these out, right, and if I just run this section, right, if you look at the scan 1 x coordinates, you can see that it's a, actually if you it's difficult to see here, but if you look at the workspace, you can see it's a row vector. It has 1 row and 180 columns, right? But if you read this, right, you need a m by 3 matrix, which means you need to convert this row vector into a column vector. Basically, your x coordinates should be one column, your y coordinates should be the next column, and your z coordinates should be the third column, right? That's how you can create a m by 3 matrix, right? So what I've done is I've just found the transpose, right? This little apostrophe here transposes these values, right? So instead of a row vector, now we have a column vector. So I put the scan 1 x values as a column vector, the y values as the second column vector, and the zeros as the z column vector, right? And I've done the same for the 32nd scan as well. And then what I'm going to do is I'm going to use MATLAB's point cloud function and input as an argument the first scan and the 32nd scan. So I get 2 point clouds, right? And I've also added these additional arguments here, which can give colors to the point clouds, right? So how that works is for each of the points in your point cloud, you can give a particular color, right? Again, the documentation is here. Should have a section about color somewhere. Yeah, you give color, and what you have to do is you have to give the color in terms of RGB, right? So you can see here I've set the out of the columns red, green, blue. I said red is 1 and green and blue 0. So our first scan will end up in red. And for our 30-second scan, I've made the green column 1 and the rest 0, which makes our 30-second scan green, right? So if I visualize this, right, so when you have a point cloud object, the way you visualize it is using the function PC show, right? Again, in the documentation, you can see that they've used PC show here, right? So if I now visualize the 30-second scan and the first scan, it will look something like this. Right? So now we have a 2D point cloud. The red represents the first scan, the green represents the second scan, right? So you can see that this is a 2D point cloud. So you can imagine the robots at the center, and it's made 2 different scans of the environment, right? Actually, it's made 2,726 scans, and we've only picked the first and the 30-second scan. Right? All right, now that you have 2 point clouds, you can do ICP to figure out what the rigid body transformation between those 2 point clouds are, right? And lucky for us, there's just one line of code. You just use this function called PC register. Again, the documentation can be found in this link. And you just need to input the 2 point clouds, right? And it will give you the transform between this point cloud and this point cloud, right? So if I run this now, we will get an answer to the transformation between the 2, right? But before I run this, can someone guess what the transformation looks like? By just looking at this image, what sort of transformation can we expect? Is there going to be a translation here? No, right? It seems as if the robot has kind of either stayed in the same place or rotated in the same place. So your answer shouldn't have a translation. It should just be some sort of rotation, right? So if you look at the final answer in what you get in in this variable T form, right? If you look at it, you can see that it's a 4x4 transformation matrix, and you can see that the translation part is zeros, a set of zeros, which means there is no translation, which is correct. What we have instead is some sort of rotation that has taken place. Also, if you look at it, the rotation has taken place in the z-axis, right? Because it's a 2D rotation around the z-axis, right? Also, there are these 2 parameters here that you can see that come in the final line. So you don't worry too much about this, right? These are what we call some sort of affine transformation. So we already know what translations and rotations are, right? In transformations, but there's also a type of transformation called an affine transformation when there's a bit of warp in your object, right? So this is a full transformation matrix that also estimates the affine transformation, but at this point you don't have to worry too much about these 2 parameters, but you should know that this grid over here represents the rotation and these 3 represent the translation, right? And that's how a transformation matrix is formed. So what we've done, just to summarize, is we've loaded a bunch of laser scans, right? We've picked out the first laser scan and the 32nd laser scan. Then we converted those laser scan range bearing information into Cartesian form, right? Added a bunch of zeros to it so it becomes 3D, right? 3D in the sense it has a third element, third set of coordinates, but all those coordinates are zeros. And then we've used that XYZ values to convert it into point cloud information in MATLAB. And then we've displayed it in this, and then used ICP to figure out the full transformation matrix between those 2 point clouds, right? So that's basically what we've done in this question. All right, any questions before we move to the last part? Is this clear? Okay, so no one's really saying anything, so I'm going to assume all of you are clear on this. Right, let me just